大家好，我是王不老说半岛。Hi, folks. Today I'm going to continue my discussion about packaging process technology with a focus on HBI, so-called hybrid bonding interconnects. That's how Intel calls it. I think it's a pretty good indication. And then I saw many roadmaps. And then, of course, we're going to focus a lot on process and then discuss about the yield issues. And that will be the focus of the day. Before we start, let's just talk about straightforward. What is hybrid bonding? This is a foil I took from the Betsy presentation. I think it summarized very nicely. Let's take a look. It has three steps pretty much. It has the die surface preparation. You have a die and wafer. This is pretty much die to wafer or wafer to wafer. Similar process, but different consequences. And then the die to wafer, of course, is a lot more difficult than wafer to wafer. Die to wafer, you need to cut it, right? When you cut it, all the chunks come out. It's not easy to deal with that, right? So, but let's focus on the simple process for now. So pretty much the surface of the hybrid bonding is that you have copper, and then this is oxide, usually SiO2. And you want to bond copper to copper and oxide to oxide. So this is a hybrid. And not just one bonding, but there are two bonding happen at this process. And you want to have a shallow, a little bit concave, convex, concave interface between copper. So you will form some kind of small void. That's by nature. They don't really want that, but that's what happened after you CMP it as a local dishing. Is that a good thing or bad thing? Actually, it's not a bad thing, you know. Then you have a void, of course. Then later on, you're gonna anneal it off, right? With some high temperature, not too high a temperature. You don't want to kill the die, right? The die cannot put up with more than 400 degrees. The die is a good die. Now that's the key thing I'd like you to remember. Everything we put it on here, they are all perfectly good die. They're called non-good die, KGD. So they are already expensive, come with a cost already. If you do 5 nanometer per se, each die is run you like a couple $100. Okay, be very careful with that. Then so you need to do some treatments, forming some of the copper pillar, and more than that, of course. And then you bond them, and then the oxide here, that's from the process as well. All these had to be bonded perfectly. Okay, and of course they come with the various process challenges. We're not going to detail for now. Right. So basically, 3 steps: surface preparation before you bond it, then you bond, then you anneal to get rid of the void. That's pretty much the 3 simple steps that are related to the HB, to the hybrid bonding. And that opens a lot of new doors. Let's now look at more in a grand scale. As I introduced today, I'm going to talk about many roadmaps, process, and yield. Let's look at the roadmaps. The hybrid bonding from this IMAX 3D integration roadmap is pretty clear. Right? So the key is to look at the contact pitch. The more advanced you go, the scaling, you go from, say, a couple of microns. Let's start to see the hybrid bonding already. Anything below 10, you start to see that happening. Of course, you could use the solar bonding to below 10. That's possible. That's still possible. But they say that if you want to move to hybrid bonding, you might as well move earlier because that you need to capture learning. And all these, at the end of the day, at the end of the ultimate connections, is the second fundamental line after stacking, right? You have almost this one. This is some micron, it's a 0.5 micron to 0.1 micron. So this is probably the ultimate you can do with this. And hopefully you can achieve that, right? That's where all the research, TD money is spent on how small contact pitch you can do. And we later going to see a lot of roadmaps. Okay, that's what the purpose of this presentation. Give you a plethora of various roadmaps that I collected from many presentations and companies. Hope you can get a good feel of what's happening. And I like this McKinsey report. It clearly shows a timeline about the packaging technology. From 1950s wire bonding to flip chip to wafer level bonding, 2.5D stacking. You have this, last time we introduced this a lot, TSV, RDL. This one we talked about this subject a lot in the last presentation. And today when we are focusing on more of the TSP area, right? This way. TSP is also here. So, I mean, not TSP, I'm sorry, the HBI, more of that. And the reason I want to show you this picture is that they also showed another picture is that it's not easy to apply because you have the JDP. JDP is called Joint Development Process, which means that the customer is going to work closely with the foundry, such as TSMC, Samsung, and Intel, to enable a certain specific packaging process. It's not an easy thing. At the end of the day, you need overall 2 years. The minimum you need to have that from the customer acquisition. You have some initial discussion about what you like to do, and then you have JDP, right? And then you have a test vehicle come out. You have a pilot, and then you go to mass production, right? So overall, you need about 2 years. TSMC just announced they built the world's largest packaging plant on Earth in Taiwan to tackle this problem. And if you remember, last time I presented this picture, it's a Xilinx 28 nanometer 3D IC test vehicle. You can see that the tape out date, all the way to maturity. It's almost two years by itself. And then here you have, a lot of other concerns, alignment meeting you have to go through. So 2 years is kind of minimum. So 2 years indeed is where you need to prepare for. And my question is, do you have 2 years? Right. So, and with that, I would like to move to talk about yield. If you look at the average die yield from TSMC, right? TSMC in 2019, they reported the average yield of the Apple 14 is about 80% for the 5 nanometer. But the peak yield per wafer, over 90%, with a die size about 18 millimeters square. So if you look at the right-hand side, the die size, say this is 17, right? So it's 0.17, 0.2. It's roughly here, okay? Roughly here is, so TSMC is roughly here, say 90% to 80%, somewhere here. And these curves are theoretical curve predicted by various statisticians about what is a yield will look like with a Poisson distribution. And this is the best case. This is the best case that you can get. And you can see that TSMC is within these curves. These are all theoretical predicted, right? They are not like the HBM data at all. They just say if you have Poisson distribution of your particles and your die size is this, then you have this relationship with a certain probability distribution that you assumed. And these are all basically certain type of Poisson, and then a derivative of those Poissons they introduce to fit their own data. And you can see the TSM is pretty good. They are all pretty close to the theoretical limit within the range. And then the other guys is far below, right? TSMC, Intel is somewhere, I want to say somewhere here, but they are far below Intel because the customer sees that. That's why they go to TSMC. And you know, they sometimes move from Samsung to TSMC, sometimes from Intel to TSMC, because the yield are close to theoretical limits. So it's how clean the process of TSMC. So their yield number is as perfect as a theoretical curve can be. But look at the number. Even that is like 80 to 90%, right? But what about packaging? If you look at the packaging, this is what they reported. Douglas reporting on the in one of his talk in the in his virtual conference 2020, 2021 during COVID. You can see that he reported the yield is 95% with 91 millimeters square and 100% for 110 millimeters square. This does not make sense from this curve. This curve clearly shows that if you have die size, it has to go down as the die size increases by these theoretical predictions. None of the prediction will say the other way around. Say at the larger die size, you may have a better yield. It doesn't exist. Okay, and then the number is like way here, and here you have 100% yield for larger die size. So that just does not make sense, isn't it? Right? And their yield, it has to be 95%. Wait a minute. This is what you require basically because the die you put it on, they're very expensive. 5 nanometer each one is already, is already very costly already, a couple $100. And of course, you want 100%, of course. Yeah, that's understandable. But can you do that? Okay. So my explanation for that is that die yield versus packaging yield can actually be different. Die yield particles are random with Poisson distribution. So the way we're going through chambers, they see particles. Particle is an avoidable event. You cannot get rid of it. You cannot get rid of it 100%. You can get rid of it to the best you can. And it's not possible to yield 100%. And that's the reason why larger the die, smaller the yield. The reason is because if you a big particle landing on a big die and you kill that big die, of course the yield number he got hit very badly, and that's what I showed last time. That if you use the NVIDIA chip about 8 centimeter, their yield is like here, right? It's off the chart already. It's like 30%, something like that. That's or less. That's what the big die like NVIDIA got. And that's what's happening actually right now. Right? That's because your die is so big, meaning that you're so vulnerable to the attack from the particles. But packaging you are different. As all dies are non-good dies. They come in good die. When you go through the process, they should have only systematic errors, not random errors. The random errors with Poisson distribution, meaning that you cannot yield 100%. You always have something going to kill you. But for a packaging world, you have only a few dies on a big wafers, a selected limited number of dies, and you're looking at a process, say couple bonding, hybrid bonding, and that in some chances or other bonding, you could 100% okay. So to me, they could have only systematic errors. They should have only systematic error, not random error. That is the assumption here. That's the reason you can see in many cases, packaging yield could be 100% because their distribution are fundamentally different on the die yield distribution. Right? And then I could also ask you, what does die size matter? In here, of course, die size matter. And in here, packaging, die size matter. Let's look at this question. Die size among applications. This is Gao presented in the last year's ECTC. It's a semiconductor die size with your heterogeneous integrations. And then HPC is what we saw here, right? Larger die size, very large. And here is a NAND flash memory about 100. And then the HPC, high performance computing, FPGA, these huge dies, this is H100, A100, the NVIDIA chip, huge. So when you do integrations, does it matter with will that impact to yields? That is this study. This is what he summarized. I think this is kind of not exactly a roadmap, but it's a big picture that I think you will enjoy. So Gao is from Adeya. Adeya's company is like an IP company. It did its research, and then it's pretty interesting. Their result shows that they cut the die, right, called singulated, meaning they just dice the die with all kinds of key methods that create different particles. And then they do so-called HBM process, which means they did it in the foundry. And the die size 3 by 3, 1 by 1, 0.5, 0.4 by 0.4. This is not that big. It's about 9 millimeter, right? 9 millimeter square. So this is roughly the same as the what TSMC reported, 91 millimeter square. They have a 95% yield. And I think the results of this is trying to show that there's no difference between the yield of these three dies. They all bonded successfully with the die-to-wafer bonding, so the hybrid bonding. So this means that die size does not seem to matter that much compared with the packaging, compared with the die yield that compared to this one. So die size matter to this? Probably not. Probably not that much. They don't get me wrong. There are some concerns as well, but that challenge is not as bad as the die yield here, which is this is theoretical. Okay. What I meant is that if your die size like H100 Hopper, there's no way you can get 90% die yield. Just no way. All right. The best you can do about 30, 40. That's it. There's no way you can come to say, I'm on a 90% yield if I work very hard. It doesn't work that way. It can't. Okay. But packaging, you can't. You could do it. The reason is that TSMC already did it. Right. They have very high yield and for very large die size. If you remember that they right now can do packaging, they go to do 5 or 6 the field size, right? Right now they can do about 3 die size maximum, which 858 by 3. So that's very large. And they don't report a bad serious degradation of yield. And they can move to 5 to 6x of the maximum field. So we can see that this one is not a super concern. It's a concern. You got to be watch out as well, right? But it's not a super concern. So that's the yield perspective. Let's look at another perspective. This is a cost perspective. Well, as we know from last time we introduced that at 7 nanometer, this trending break away. The cost is very, very high. That's what. So rule of thumb is obsoleted at 7 nanometer spike. It's AMD's report. Okay, and that just triggered my thoughts on what I saw from the Min-Chiang Kuo's his medium. He's talk about will Qualcomm drop Intel at 2 nanometer? That's quite a good question. Nobody really know what what happened, right? But there's rumor says that. Well, it's not there's rumor. This is his analysis. He says that cost of IC design after 7 too high. Yes, it is too high. So you can't work with more than one customers, one foundries. So Qualcomm, you want to do you want to do, you want to say, hey, we're going to work TSMC and Intel at the same time, see who's the best, who's better. Doesn't work that way because that's a huge 2x cost. Okay, so almost 2x cost. And then Qualcomm has been working with TSMC and Samsung. And then right now, the market downturn, and now are they going to have, does it have enough resources to work with Intel? Do you remember that? That's what I uh, keep telling, keep saying that. Yeah, you need 2 years, right? You cannot just say, oh, today I'm gonna work with Intel. If you're not happy, I move to TSMC tomorrow. It doesn't work that way because it takes 2 years. So you better make a decision now. So you have it. So you could have a product in 2 years. If you work with Intel for 1 year and say, "Oh, I don't like it. I'm sorry. I'm going to move on to some other supplier, some other foundries," then you lost a year, right? So you want to do it. You better do it quick, right? So that's where the rumor comes in, where Qualcomm dropped Intel too, because they have to pretty much decide now or in the very near future. Okay, that's a problem. Working with this new packaging technology, it's just a long process, right? And you look at the future of 3D stacking. Okay, then we are in a TSV pitch going smaller and smaller from the big dot to this fine dot. We are going to this pretty much die to die or die to wafer area, right? So that's what the hybrid bonding can do. So pretty much the hybrid bonding, if you look at this Intel 2021 presentation, it says very nicely, it's comparing the coarse pitch sorter, which is TSC, the thermal compression bonding, TCB, thermal compression. And the other one is the HBI. You can see the difference between them. Here, you cannot, this is copper and then this is solder, right? You press them together and then you form a die. It's very easy to see that the packing density versus the packing internet connect density. This is much, much smaller than this one, right? A factor of 10 to 100 or more. So this is the reason that that people will have to move to hybrid bonding. And so then you ask the reason, why is that? That's what thermal compression bonding versus hybrid bonding, the solder attached. Here is this the thermal compression, that there's a copper pillar and then there's a solder. A solder is on top of the copper bonding and then you press it down, all right? And then you reflow it. You heat up to some temperature to melt, exactly melt the solder, but semi-melt the solder. A reflow means that the solid become a liquid-like material at temperature below the melting temperature, like your eutectic temperature, something like that. Right? Then you fill it up. And hybrid bonding, on the other hand, don't have that. They don't have the bond. They're missing the solder bond. It's just like copper to copper. And then they attach in roughly the room temperature. And then you have you have high temperature anneal to get rid of the void. And here you did some work here, which we're going to discuss previously, right? What we discussed earlier is this, right? This is the first step of hybrid bonding. The goal is to have copper interconnects and then the oxide interconnect. They all connected and bond. There are two bonding happening, copper bonding and the inorganic passivation. That is just a treatment before you bond them. Everything has to be super clean. All right, that's one thing. Not just super clean, but also hydrophilic. You cannot have hydrophobic surface. You have a hydrophilic, which means that they will be super active. Let's put it that way. They are like water. If you see a surface hydrophobic, they are not activated. They don't like to stick to each other. You want something to stick very well by just bonding them together. Immediately form an easy van der Waals bond. That's a weak bond, all right? And then later on, heat up, become a covalent bond. And that's a strong bond, okay? So, um, so that's the what I meant, that TCP versus HB, these two different processes. And why TCP cannot be scaled? The thermal compression has a problem. If you open up closely, you can see that when you want to scale solder this process technology, then you have to be concerned with the thickness of copper pillar. The more you scale down, right, you have to make it thinner, rather, and then shorter, right? Then you had to be the height of everything had to be reduced. This means that you have a mechanical control problem. You have a manufacturing tolerance issue, especially from reflow, right? Reflow to make it soft, right? You make it soft. And this process is not easy to control. So you got to give it some leg room, cut them some slacks. And that's a problem. That's the reason you can see from the Intel presentation that the density here is much smaller than this one, right? So this one is a much larger density than the solder one. And the reason is, of course, I mentioned here is devil in the details. This small thin coppers, all right, and then solders. When you get smaller and smaller, it's harder to get that perfect shape that you want. And it's less forgiving. So that's why you lost the control of manufacturing tolerance. So that's the problem. So you have to open up a room for them to make errors, right? So this is a bump out, right? How can you control that? You control the material, but how can you control perfectly the height? They're all difficult challenges. And on the other hand, copper pads in the hybrid bonding, they are much more, if you do it right, they don't stick out, right? They are planar. They are called planar. So they don't have this bump reflow issue. So they don't have this swelling, this swelling issue. They don't have that, right? So they just have the wrong attachment and then later on the anneal. So if you could align them properly, so they are very important in aligning these copper pad. And these are micron size. So it's not too difficult, not too difficult. So that's why their manufacturing tolerance are greatly improved. And they could do a better job when scaled. And this is a picture that Intel presented. They think thermal compression is doing up about, say, 15, and then the hybrid takeover. So that's why T25. But in reality, I mean, solder bomb can do here, right? Some people I saw can do here. And hybrid is that, of course, and people start adopted below 10. Okay, so this kind of a, oh, that's why Intel presents it. It's kind of a very forgiving, very high level. Okay, and let's look at tools. Who is doing what, right? Betsy and then the EV group. So all these key tool supplier from Europe, pretty much. They're pretty much dominant market. And then the Xperia and then Adea, they're kind of IP company. They will do design process with you because there are a lot of experiences. So it's a hybrid bonding machine, a thermal compression machine. And you go and look at the spec of one of the Betsy's tool. This is called Chameo, 8800. The one that shocked me is this. This is ultimately what they want. Huh? What it means that you need to have a very high accuracy, less than 0.200 millimeter, 200 nanometer. And then the newest one I saw is less than 100 nanometer now. So the mechanical control accuracy is highly, highly important. And also the speed. You need to have a couple thousand units per hour, this kind of accuracy. The thing seems flying. If you can imagine, the robot take a die and put it on a wafer, for example, right? They need to have less than 100 nanometer accuracy. And then the process is everything is super clean, assume super clean. Then the robot is moving inside to everywhere. And then you have to have 2,000 units per hour, this kind of a throughput in order to make money. And a super clean environment. That is challenging. So this is what they're advertising their 8800 can do. Okay, so that's what they claim they can do. Whether they are in high production and generate product or not, I don't know. But that's what they claim they could do. From the track record, it seems they can do that, no problem. And you look at the head here, they call it the patentee Van Gogh bond head. All right, so this bond head, it's they have some tweaks around, but the general, this is not exactly the same. But this is what happened in the bond head area. In the die transfer, you had the substrate is a wafer, you heat it up and you cool it down at the same time because you want to maintain the constant temperature. And you have tons of optics. You move things around. You need to let the robot know where you're going. So you use the lasers to see where you're going, right? And you bond, right? This is how you bond it with certain pressure, like how many Newton you want to put it on, right? And then what kind of environment is that? You cannot have very high oxygen content because copper will oxidize very easily in air. So you demand that the O2 be less than 100 ppm. So the whole thing has been in vacuum, right? And you move your robot inside a vacuum. Not a thing that easy to do. And then at the end of the day, you need to have less than 100 nanometer accuracy. Okay, so that's why it's challenging. Very few companies in the world can do that. EVG and Betsy seem to be the big boy. Okay. So let's now do a little bit more actual process. HBI is a hot topic. Direct couple bonding, hybrid bonding interconnect, or HBI. That's what we try to discuss. And Betsy tool set. Come back to Betsy again. Sorry about that, but they do a pretty good job in summarizing what we want to know. These are all aspects of his tool sets, what they can do. Okay, and here is the hybrid bonding. The other, these are the other type of bonding. This is this one even more advanced, embedded bridge die attach. Wow. Okay, because you can see that the reason I want to present this is that actually they did a lot of research to enable this process. Foundry is using their toolset that's to integrate into the flow. And then both are equally important. Now look at the packaging big player in the world. There are only three, right? Pretty much. Samsung, Intel, and TSMC. And then look like right now TSMC is ahead of everybody. And they are using all aspects of this tool set. And you could argue that, well, Samsung and Intel, they could also buy the same basic tool set, have the same fundamental capability. But why they cannot compete with Intel with TSMC to get the packaging process that TSMC has right now? Well, that's a good question. You could have EUV, right? Everybody can buy EUV, but it does not mean you got the best out of the machine. And EUV yield per se, right now, TSMC has a number one yield. So similar situation happened. The tool supplier provide the tool basic fundamental capability, and the foundries, you buy them and put them into process, integrate these machines into their process, and then and somehow comprehending all the aspect, right? All the process variations, optimizing them to make a good thing out of it. And TSMC right now seems to do a pretty good job in that. If you look at the flow-wise, this is process flow, wafer to wafer. Then this is what Letty shows, wafer to wafer flow. When you align them together, you need a very good edge placement, very small edge placement area, right? You align them properly. So it's not too hard, okay? And then the 10 micron pitch is where the hybrid bonding starts to shine. And actually, the hybrid bonding, as I explained, is a molecular bonding of copper and SiO2 surface between the two, the top and bottom wafers in this aspect, right? This is direct bonding, direct hybrid bonding. They bond it together, then before they bond it, you make sure it's super clean. And when you contact one of the walls bonds, right? When these two wafers bond together, one wall falls kidding. They form some kind of a weak adhesion before they change into covalent and metallic bonding, right? The covalent bonding is between SiO2 and SiO2, right? And then the metallic bonding is for copper. And then that's after thermal anneal, couple hundred degrees. And if you go to die to wafer, I think this picture is a simple one from TSM, from Intel. I like it. So what they do, you can see that they polish the both sides to expose the copper and SiO2, and then you singulate, which means you cut the wafer into dice size, and then you put it on top. So that's pretty much what you do. And this is a big picture, a simplified die to wafer flow. If you look at the more detail wise, this is from Letty, that you CMP it, right? Wafer to wafer bonding. And then the also die to wafer bonding is also you CMP it, and you dice it, and you holder placements, and you're cleaning it. And then for the bottom wafer, you do a plasma activation because you want to activate the surface, right? Then you stack them. So this means that the die has a cleaning. Whether they're going to have plasma activation is hard to say. It's hard to say. All right. It doesn't show on the picture. Every process, I believe TSMC or Intel, they may have their own thoughts, but then they need to activate it before die to wafer attachment. But definitely the bottom one will have to be plasma activated. Usually that's what happens, unless they are so sure the surface is so clean, they're so hydrophilic. All right. And this is what I showed in the first page, right? Let's review that. You die, CMP it, you have this tishing, unavoidable, I'm sorry. And then you have inorganic passivation between SiO2 and copper interconnect. And then you anneal it out, right? To form a perfect die to wafer or wafer to wafer. If you look at more closely, this one's is talking about the anneal. So process-wise, you see that it's only less than 150 degrees, 100, say 120. That's all you need to do to bond SiO2. But the copper, you cannot, right? You cannot that easy because copper require a diffusion, interdiffusion. You need a copper atom to move around and get rid of these vacancies. All the vacancies need to move out by the interdiffusion of copper. So you need a temperature slightly below 300. Can you say, well, can I do 400? No, you cannot do 400. The reason is that the die you have is a non-good die. They have a lot of back-end process already, and that's copper inside the non-good die. It's a bad idea to heat up your wafer, your die above, 400. It's very, very bad. Right? 300 is kind of pushing already, so they don't want to do 300. You're doing like 200, 80, something like that. Because the higher you go, then you have a reliability problem. Right? Be very careful. So this is from the anneal perspective. High temperature anneal and then low temperature anneal is for the dielectric fusion. It's very easy to do. As long as your SiO2 is very hydrophilic, you have OH bond everywhere. It's nice. then bonding is reasonably easy. But that does not say the same to the copper. Copper need to move around, so you need a higher temperature. Okay. So in short, I could see that the process control, you have different flavors, is a local variation sigma, which means a die flatness, local recess. This from CMP, right? And the roughness of those pads. These are CMP related. How flat the dies are. The larger the die could be, it's not easy to keep it flat. So die size matters in this aspect. And then die size, a local recess on the pad. That from the CMP wise, that would be related to CMP erosion, not dishing, but erosion, right? But it's all CMP related. So die size may, play some role. I will agree to that. The global, I would call it a global variation, just a fancy name. What I meant is that when you have very large wafers, dies, then the wattage of the wafer should be an issue. So you want to connect something to something else. The wattage of the wafer from the die itself, on the wafer, or wafer to wafer, the wattage could be an issue. That's what I meant. And lastly, but not least, is the zero defect. Because you have non-good dies on top and bottom, right? And then you are moving machines, as I explained to you. The machine is moving very fast, high speed, 2,000 units per hour. That's a couple seconds per die. So you can imagine that's how fast things move around. And of course, you need to have a zero defect in a way that the particle size has to be much smaller than your copper feature size. You cannot remove the particle completely, of course, but suppose your copper your copper pillar is 10 micron and you have 100 nanometer, 10 nanometer, it doesn't really matter, right? Your particle is 10 nanometer, 100 nanometer, doesn't really matter because your copper pad is 10 micron. But if you scale it down, say, I want a copper to be 200 nanometer, then if you have a particle that's 100 nanometer in size, that impact will be different. The yield number not going to be look good. Okay, so this is where the things come in. That the moving machine parts, they generate particles and they disturb a linear flow of clean air. Right. So that's why what I'm trying to say is that the demanding of hybrid bonding is going to higher and higher when you scale the device. And let's look at this just example of the substrate warpage, right? It could change. This example is a microbond. It's not hybrid bonding, but just to show you the flavor. If you have substrate bending because or either from the top die or from the substrate, you're gonna have problem. Or this your die tilt, all these give you problem. And then you will in some aspect you got solar bridging because of that. So that's just to show you a flavor about what I call a global variation sigma. All right. When the sigma is which means that the process window 3 sigma is what you would like to control, and then the 5 sigma is the range that you like to control. So all these have to be controlled, right? Mechanically have to be controlled. If you don't control it nicely, you have bridging. This is a solar bridging, but you can imagine the copper pad in the hybrid bonding bridging. That's also bad. But currently, the UOS, this consulting company, they show that the hybrid bonding interface, the 9 micron pitch has been done very nicely. Die to wafer bonding, okay, they call it's HBM data, so there's no problem. So people seem to do, 9 micron seem okay, especially TSMC, okay. But HBM, hybrid bonding in high volume manufacturing, this HBI means high volume manufacturing. High volume manufacturing means that it drives new specs. It requires extreme clean capability. And this, you want tools to be super clean, but it's in the front end environment. All right. And then you have the very accurate place in a nanometer scale. All right. All these. And then your die is, it could be very small and very thin. So this is challenging. If you put a big die and you want to hold on to it to an accuracy that we showed it last time here, 100 nanometer accuracy, right? If you have a big die, it's really easy. You have a super thin, small die. Imagine your robot hand gonna move around with that stuff. It's not an easy job. Okay, so you need to improve your machine to do all the things. That brings me to the dark side of hybrid bonding. Okay, it had many issues. The more you scale, you're gonna see more the CVMP issue, copper field issue, oxide depth issue. And then the copper oxidation at room temperature, is that going to be issue or not? And then extreme cleanness. And all these leads to higher cost. Okay. My question is that going to be exclusive to high performance computing? All right. Let's look at the summary that in many areas, hybrid bonding need further investigation. This is from Betsy. I think they did a very good job summarizing this is what they saw at that time, what all those various issues. The copper quality and field, because copper generates stress. All right. So you have a lot of these structures. A copper field here. Everything you do something to a wafer, it generates stress. Different process give you different stress. And whether that stress is going to be good or bad depends. So its quality and feel could really impact your subsequent process. Okay. And your oxide deposition also had the problem, right? You have to be super flat. This is a very easy cartoon, right? Very easy cartoon. And so they are all equal thickness. But in reality, they may not. If you have different heights, then you're in trouble because you cannot form a bond, right? So that's concern. If you don't form a bond, you have a void here, and copper can go in here. Then you have a copper to copper pad to copper pad to copper pad, contact, right? And bridging, just like here. Here is solar bridging, but imagine copper bridging could also happen because of that. And CMP dishing, this is all problem that even the silicon CMOS has it. The dicing are different. We don't have dicing in our regular silicon CMOS flow, right? We don't have that. But you can see the particle generation. If you generate this mechanical particle, how do you clean them? Very efficiently. What happens if they fall into inside these trenches? Then you got a problem, right? And then plasma activation. How do you make how do you optimize the surface? You have used oxygen plasma, your nitrogen plasma. People play all kinds of plasma to activate the process so as they can bond properly. And bonding, even bonding geometry plays a role. So you could say, I want to make this bottom a little bit bigger and top a little bit smaller, so coming easy to bond. Okay, so all kinds, and then want to change the surface to SiO2, SiCN. Yeah, you could all play the game. And then this is what they claim you could do quickly, right? So all the bottom line is integrated process flow, low particle, and you got to check it all the time. Anneal, all right, and then a line between pads that will change your electrical property to in the capacitance to some extent. At the end of the day, lifetime is critical. I would like to summarize all these into three categories. Is learning from backend online. We already know a lot of problems in regular CMOS flow, and we have solution for that. Copper fill, we know how to do a good copper fill. CMP, we know is a problem, so we do a lot of dummy structure, and then that. So we have a solution for many of the problems that we could learn from the backend online process. And outside that, of course, reliability, we studied through teeth, right, to many, many years. We know if couple line two thing, we know what happened. Learning from SOI, a silicon on insulator process, is that surface treatment. When we bonding SOI, that bonding two wafer together, we have all learning from Soitec, right? That from the global crystal. All these guys know how to bond two wafer together. The surface pre-treatment before mono-wall bonding, all kinds of surface treatment, and the thermal anneal, right? How high temperature you need to apply to get a perfect bonding between two surfaces. These are a lot of learning, a lot of paper, a lot of research done on that. So that's not too bad. The new issues is particle quantizing and from moving parts, your bonding geometry. These are kind of new to hybrid bonding, right? So that's why that's what I want to show you. Have this one I have put it separate them into three categories: back in the line, SOI, and new. And I think back in the line, I think everybody Intel, everybody is the same, roughly the same. They know what to do. And in learning from SOI, these are not that difficult as well. So they're okay. You do some tests on DOE, you figure out. The new issues are more challenging. Okay. But supply can do that. So integration of all these problems come out with a very good solution at scale. The key is at scale with 100% yield, right? So that's what you want to do. Remember the picture I want to show you is the 100% yield from the GSMC, right? 110 millimeter, 100% yield. And that is the key. You have to have about 95% to 100 because the 5% loss, and that's a lot of money because you put a good die, a good non-die on this process. Okay, so the challenge to regular CMOS versus packaging are different. The yield number has to be super high, even though the process seems not too difficult. But you're pushing the cost to you want everything super clean. So at the end of the day, you want to have a super cheap, not super cheap. You cannot have a super cheap process anymore. You capture all the learning from the regular CMOS world, and at the end of the day, your cost is going to be higher and higher. You look at the machine provided by Betsy, and you can see that the cost picture won't be pretty, right? So this is their cost. This is a new machine, and it's going to be more expensive than the previous generation, for sure, right? So that's that brings me to the end of my talk. Pretty much, I show you various different type of roadmaps, pitch interconnect pitches, die sizes, and all that. Process, not too complex, but the yield is a big question. Okay, so this concludes my talk. Thank you very much.